Welcome to 5-Minute Tech Today. Think of your computer's CPU as a highly stressed traffic controller, constantly bombarded with dozens of simultaneous demands from the software. If this controller hesitates or misroutes a request, the entire system risks gridlock. It has to decide the exact order of execution in milliseconds to keep your machine from freezing. The most intuitive way to solve this routing problem is to apply the rule we use at the grocery store, a strict first-in, first-out line where nobody gets special treatment. But mapping this human concept of fairness directly onto a high-speed machine introduces a hidden risk that cripples system efficiency. In computer science, this approach is called first-come, first-serve, or FCFS scheduling. It forms a straight-line queue where the execution order is dictated entirely by the exact millisecond a task arrives. It operates on a strictly non-preemptive rule. That means once a task locks into the CPU, it cannot be paused, interrupted, or swapped out under any circumstances. On paper, this rigid system has clear benefits. It guarantees absolute fairness, ensures no task starves while waiting for attention, and requires almost zero computing overhead to manage. However, by eliminating prioritization entirely, the algorithm sets up a mathematical trap waiting to destroy the system's overall throughput. Let's look at this animated diagram to see how it performs under standard conditions. We have three standard tasks, P1, P2, and Key 3, arriving at the CPU in staggered 2-millisecond increments with similar processing requirements. Task P1 arrives first, locks into the processor, and runs uninterrupted to completion at the 5-millisecond mark. Task P2 occupies the next block from 5 to 8, followed immediately by P3, which finishes at marker 10. By subtracting the arrival time from the final completion time, we calculate the turnaround time for each task. That gives us 5 for P1 and 6 for both P2 and P3. When we isolate the pure waiting times, the milliseconds spent sitting idle before execution, the numbers remain incredibly low, topping out at just 4 milliseconds for the final task. In a perfectly balanced environment with equally sized tasks flowing in steadily, a strict linear queue remains highly functional and mathematically sound. But watch what happens when we modify this diagram to introduce a chaotic stress test variable. P1 is no longer a small operation. It is now a massive, heavy, CPU-bound process that takes hours to complete. Because first-come, first-serve is non-preemptive, the system lacks the authority to pause or bypass this massive task. The tiny, fast operations get permanently trapped behind the monolith, forcefully driving up the average wait time of the entire system. Computer scientists define this specific systemic breakdown as the Convoy effect. A single oversized variable destroys the efficiency of the strict sequence. When forced to handle asymmetrical workloads, absolute equality in routing fails. If this algorithm were running your modern interactive computer, the practical consequences would be immediately obvious. A heavy background update would hoard the entire CPU, resulting in a completely frozen mouse cursor or an entirely unresponsive screen while the system ignores your inputs. This interactive nightmare contrasts sharply with batch processing environments, where massive sets of uniform tasks are compiled sequentially and human interaction simply isn't required. Those highly predictable, closed-loop environments remain the only safe habitat for the FCFS algorithm. Modern operating systems have completely abandoned FCFS for primary CPU scheduling due to its inherent vulnerability to these unpredictable wait times. Yet, computer science programs continue to use it as the foundational baseline for teaching system architecture, because studying its failures exposes the core logic of processor routing. The engineering lesson here is counterintuitive. Strict, unwavering fairness and processing rules does not equate to overall operational efficiency. If you liked the video, hit subscribe, and thanks for watching.